Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome students to the Computer Architecture and Assembly Language class. Today we will continue the same pipelined processor design topic. And here, this slides, it again introduces the concept of pipelining using a horizontal representation, which also called pipeline timing diagram. Okay, so on this vertical axis, which is on the left side, we can see that there have different instructions like load word, store word. This is R type addition, this is R type subtraction, and this is branch instruction. Okay, so on the horizontal axis we have clock cycle 1 through clock cycle 9. So the colored blocks, these show which functional unit each instruction is using in each clock cycle, so which we earlier discussed in our last lecture. Okay, so we are already familiar that this is the instruction memory, which is used during the fetching the instruction. Then we have the register file. Okay, then we have ALU unit, and then we have data memory, and then again register file. Okay, so this diagram shows actually the assembly line and in each action. Okay, and because the time flows horizontally, which is from left to right, okay, across each clock cycle, and each instruction progress is shown as a horizontal sequence. Okay, so that's why this is called horizontal presentation. Okay, so here in this slide, it builds on the horizontal presentation we saw earlier and formally introduce the 5 steps or 5 stage MIPS pipeline. Okay, so an instruction pipeline is like an assembly line for instructions, just as a car assembly line has different stations, for example, engine, its painting, wheels, testing. So our processor have different stages that each instruction goes through. So this diagram basically it shows which instructions occupy which stage at each clock cycle. So the pipeline have 5 stages, which is this instruction fetch, instruction decode, execute, memory access, and write back. Okay, then so you can see that ALU instruction skips the memory instruction, this one. Okay, and also we see that here also this instruction is being skipped. So store word instruction skips the write back stage here. Okay, so these two are ALU instructions R type. Okay, and these are skipping the memory stages because they do not utilize that component during this clock cycle. And then we have the different instruction examples in this slides. Okay, like this is the load word, which is load type. This is again load type. So this is immediate ALU, which is OR operation. Okay, then this is the R type subtraction, and this is the store. Okay, so ALU instruction skips the memory stages, but that means they do not use memory for memory access. So they might still go through the memory stage as a pass through and then write back to write the results. Okay, like this one. So when we utilize such type of diagram for the pipeline, so up to 5 instructions can be in the pipeline during the same cycle, and this is instruction level parallelism. Okay, because the same type, same cycles and same stages are used for the different instruction. So here you can see, for example, at this clock cycle, up to 5 instruction can be in the pipeline. So here you can see that this first instruction is in the write back stage. The second instruction is at the memory stage. Okay, so these two LU instructions are in the execution and identification stage, and this last one is the instruction fetching stage. So up to 5 instructions can be in the pipeline during the same cycle, and this is called the instruction level parallelism. Okay, and this here on this axis is again the time, which is t plus 1, t plus 2 means it is clock cycle 1, clock cycle 2, and so on. Okay, this slide shows the single cycle data path, which we have already covered. We are revisiting it briefly to contrast with the multi-cycle and the pipeline design. So we get familiar that how it is being converted and what was the drawback in this, that why we need to introduce the pipeline system. So the single cycle data path has one major problem which we discussed multiple times earlier, that all instructions takes the same amount of time and the time of the slowest instruction. Okay, so the slowest instruction, that time is the time which is to be used for all the instructions. Okay, so these are the different components which we are familiar, which is like the instruction memory, then the register file, ALU, and then we have the data memory. Okay, so here we have sign extended, and then we have shifter, which is shift left 2. Okay, then we have program counter, we have this adder and one adder we have here. Okay, then we have different control signals in single cycle, which are destination register. Okay, then we have other like branch. Okay, that enables branch. Then we have memory read, then we have memory to register if we want to select the data to register, right? Then we have for the ALU operations. Okay, these are the 2 bits. Then we have enable data memory, right? ALU source, which is the second ALU input. Okay, and then we have register write, so to enable the writing in register file. Okay, so this we also discussed earlier, that we have 2 adders in the single cycle data path. Why 2 adders? Because in single cycle, everything happens in one cycle. Okay, so the ALU is busy doing the main operations like add, subtract, address calculation. So it cannot also compute the PC plus 4 at the same time. So we need a separate adder just for PC increment. Okay, because we need to do everything in one cycle. Okay, so in the multi-cycle, we have seen that in the multi-cycle, we reduced the cycle time, and then we also reduced and removed some duplicate hardware like adder we removed, and we combined these two memories. Okay, okay, but if we compare again, then because we need to incorporate the same type of hardware for the pipeline processor design, so we will see that how it is used there. Okay, so in this slide you can see that we introduced the pipeline registers, which we already discussed a bit earlier in the last class. So the additional hardware that makes pipelining possible, this is these pipeline registers. Okay, so pipeline registers are actually buffers placed between the stages. Okay, So they hold the data that flows from one stage to next. So in a 5-stage pipeline, we need 4 set of pipeline registers. So the first one is between instruction fetch and instruction decode. That's why it's called IFID, instruction fetch, instruction decode. Then we have between instruction fetch, instruction decode, and execute, which is IDEX. And then we have a register between execute and memory access, which is X and mem. Okay, execute in memory. And then finally, we have one pipeline register between memory access and write back, which is mem, and WB, which is memory and write back. Okay, why we need these pipeline registers? We discussed earlier that in single cycle or the multi-cycle processor, we don't need these registers because each instruction completes before the next starts. But here in the pipeline processor, multiple instructions are overlapped in different stages. Without pipeline registers, the results from one stage would overwritten by the next instruction in the next cycle. So that's why if in that case, data would be lost between stages. So pipeline registers save the state of each instructions and move from stage to stage. Okay. Okay, now what these pipeline registers hold? So actually, these pipeline registers are wide enough to hold data coming in. Okay, this means each pipeline register must be wide enough, means it should have enough bits to store all data and control information that the next stage needs. Okay, so that's why you can see that here the bits are also mentioned, that for example this pipeline register should be 64 bits, this should be 128 bits, it should be 97, and this should be 64 bits. Okay, so remember that as we discussed earlier, so destination register is not included in these bits. So that we will see again in the next slide, that how we incorporate that and how that is used. Okay, so this slide, as we discussed in the last lecture as well, that this address a critical question, that how does the pipeline remember which register to write to in the write backstage. Okay, because from here it needs to write back in this register file. So how it should know that to which register it should write for that particular instruction? Okay, so from where this problem came, so in a pipeline processor, the destination register is known in the ID stage here. Okay, which is the 5 bits. So bit 15, bit 11 to 15 for RD, or bit 16 to 20 for RT. It depends that on which register, destination register is being used. But the write back stage, which happens several cycle later, okay, you can see that it happens after some cycles, after execute and memory access. So if we don't save the destination register number, we will forget which register to write by the time we reach here at the write back stage. So for the solution is that we pass it through pipeline registers. Okay, so after this stage we pass it from here, then we pass it from here, we pass it from here, then we will be able to know that at this stage that what is the destination register which where we need to write data. Okay, so what we need to do in that case, that we add 5 bits here. Okay, 5 bits here and 5 bits here. Okay, so this will still be same because here we don't need those 5 bits. So because since destination register is identified at this stage, so from here to onwards we need to add 5 bits here. So this was 1 to 8 earlier, so by adding 5 more bits it will be 133, this will be 102, and this will be 69 bits. Okay, now if we visualize the data flow, so here we see that at if it is not yet known that which instruction to be fetched. So here it is known. So from instruction bits, we know that this is RD or RT, and from here onwards, we add those 5 bits. Okay. Uh, now, now why we have the each pipeline register have different bits, because at each stage we have different type of data of different width. Okay, so we have this different number on each pipeline register. Okay, so actually, so these the pipeline registers are the glue that holds these whole pipeline together. Okay, this slide continues from the previous one and emphasize a key role of pipelining, that the destination register number must be pipelined, means should be passed from instruction decode stage to write back stage. Okay, so the destination register number is passed from ID to WP stage, and the write back stage writes back data knowing the destination register. Okay, so you're already aware that for what problem we have added this destination register through these pipeline registers. Okay, because at this stage it should remember that in which destination register it should write. Okay, so the rule states that destination register number, whether it is RT or RD, okay, it should be saved and should be passed from the pipeline registers. And what about the control signals? So the destination register number is not the only thing that must be pipelined. So all control signals that are needed in the later stages also must be passed forward. Okay, so for example, the register write, so memory to register or memory read. Okay, so these must also be passed from ID to write back stages. So if we see these pipeline registers, okay, these not only contains the register data and the instruction, so these also contains the control signals as well. Okay, so that's why in this structure we see that in these pipeline register, for example, here after the instruction fetch stage, so it pass the instruction and then next program counter to this instruction decode stage, because here we need the instruction, okay, which it decodes to get all this information, which it further pass to this execute stage. Okay, then it also pass the next program counter from here to this stage, because for the branching and jump instruction, okay, from here it calculates that what should be the next program counter, then it pass it to this program counter. Okay. So you can see that by looking to these pipeline register, that between two stages it pass the relevant data. For example, from instruction fetch to instruction decode, instruction is the important data. Okay, so it is passed from here, then from at this stage it decode the instruction, and then whatever it gets, like the data from bus S, the data from bus T, then immediate constant, okay, and this next program counter, these are passed from this stage to execute stage. Then at execute, it utilize this information, and whatever it generates for the next stage, it pass through by utilizing this pipeline register. You can see from here it is passing the data from bus D and the result from the ALU as well. And then, of course, the RD register is the part of this pipeline register, and this as well, because it will utilize it here in the write back stage. Okay, so this is how, as we mentioned in the last slide, that these pipeline registers serve as glue between these different stages of this pipeline processor design. Okay, so now we will move to the next slide, okay, which is again the single cycle data path. Okay, this is again the repeated slide, and so the same one which we saw earlier in the, I think, slide 53. So we are revisiting it to make sure that you understand the baseline before we move it to the pipelining processor. Okay, so we are already familiar with all these components, which are instruction memory, adder here, register file, sign extender. Okay, then we have a shifter here, ALU controller. Okay, and then the data memory and some multiplexers here to select the data. Okay, and then you can also see there are different control signals, like which is the destination register. Okay, so it selects the destination register, either it is RT or RD. Then we have branch, which enables the branch. Then we have memory read, okay, memory to register, okay, ALU operation, okay, ALU off fields, two bits data is transferred from here to this ALU control. Then we have memory write, ALU source, and register write. Okay, so these are the different control signals, and remember that the same control signals are used in the pipeline processor design as well. Okay, so the same control signals which we are discussing here in this single cycle. So that is the reason that this slide we are looking at again and again, so that you should be well familiar that what data path component and what control signals are being used in this process. Okay, now again, this slide shows the complete pipeline data path. The single cycle data path breaks into the 5 stages, okay, which is IF, ID, execute, memory access, and write back. Okay, so in this big picture, you can see that these are the 5 stages which are glued with these pipeline registers. Okay, so each pipeline registers having different widths of data, and we are already familiar now why these all pipeline registers have the different bits, because each carry different type of data and different control signals. Okay, and then after this stage, this each pipeline register contains the destination and register number as well, okay, which is passed through ID, EX memory, memory to write back registers, which are now wider 5 bits, okay, because we are passing RD 5 bits, which is to be used from this stage to write data in the register file. Okay. Okay, so I hope that you all are well familiar now what is the data paths, different components to be used in the different stages of this pipeline processor design, and the different pipeline register, that why different bits of these pipeline register, what they carry, okay, and how they pass the data from these slides. Okay. Okay, here again in the slide 59, we see the complete pipeline data path along with the control registers as well. Okay, so this slide shows the pipeline data path and makes some important point. Okay, that the same control signal used in the single cycle data paths are used here, but now they are pipelined so that they can execute and process multiple instructions at the same clock cycle at the different stages. Okay, so uh, you can see that the control signals are also pipeline. Okay, this is also a big difference. In single cycle, control signals are used immediately where they are generated, so they are utilized in the same cycle. But in the pipeline design, control signals must be passed through pipeline registers to the stages where they are actually utilized. Okay, because at the different stage we have different components which needs the different control signals to complete the processing of that particular instruction. Okay, so you already know the step by step each stage and what the components are doing and what they needs, what control signals they need. Okay, like here the instruction memory. Okay, so simply instruction is fetched and program counter is computed and incremented by 4. Okay, then at id stage here instruction from IF is decoded, RS, RT, okay, and so it reads the data 1, reads data 2, then immediate number, okay, so these all are passed to the next stage. Okay, in this stage it reads the data 1 and 2, okay, from this step, and also get the ALU control bits, okay, the ALU source, all these information to process whatever we need to do for that particular instruction. Okay, and it executes over here. Then in the memory stage, ALU result goes to the data memory address. Okay, for load word we read the data. For store word value, b value goes to the data memory and it writes the data, and the memory write signals are enabled over here. Okay, and finally at the write back stage, so this multiplexer selects between ALU results and the memory data, which is controlled by memory to register control signals. Okay, so results written to register file at the destination register. Okay, so which was selected by the destination register, either it is RT or RD, and RG and register write. Okay, it enables the write process here in this register file. Okay, so hopefully now you understand that what is the difference from the single cycle to the pipeline. Okay, so in the control signals, in the single cycle, control signals are used immediately, but in the pipeline they are passed through pipeline registers. Okay, and then the control unit is the combinational, but in pipeline it's still combinational, but output goes to the ID and EX. Okay, and then the signal timing, in the single cycle everything happens in the same cycle, but here it is delayed from 1 to 3 cycles to match data path. Okay, the control signals are generated from here, but it might, some are used over here, some are used over here, and some are used over here. So these are the main differences between the single cycle data path and pipelined data path. Okay, now this slide, this is just showing some main control signal values, okay, and which are used from different type of operations. So these are the some important control signals like destination register, okay, register write, and this ext operation is for the zero or sign extension. Then the ALU source, branch if equal, branch if not equal, jump, memory read, memory write, and memory to register. And then for each operation what control signals hold which, what values, these all are mentioned in this table. Okay, so you can see, for example, in R type, okay, the value is 1, which is RD. Then register write is enabled. This doesn't care, okay, because there is no extension in R type. Then ALU source is 0, which comes from bus T, and then these all control signals are 0. So similarly, this table highlights that for each type of instruction, which control signal to hold what value, and wherever there is X, it means that it is a don't care, means it can be 0 or 1. It used to minimize knowledge, okay, because these are not relevant at that particular stage. It shows the control signal table for the pipeline processor, and this is one of the most important slide for understanding how control works in a pipeline. So we review the 5 stages, which are instruction fetch and PC increment, instruction decode, register fetch, execution and memory address calculation, then memory access and write back. And then here we have a control signal table. So this table shows which control signals are active, 1, or inactive, which are 0 for each instruction type. Okay, and then we have these 3 different stages, which are execute, memory access and write back, because you can see that for the instruction fetch and instruction code, nothing to control, as IM read and PC writes are always enabled. Okay, what does it mean? That instruction memory read, it happens in every cycle. Okay, so regardless of any control signal. So similarly, PC write also happens every cycle. So the IM read and PC write are the stages, okay, which are always enabled regardless of any control signals. Okay, so we only need the control signal in execute, memory and write back. Okay, and if we see here, there are the different instructions like R type, which contains addition, subtraction, okay, different logical operations. Then we have load word, stored word, and BEQ, okay. And for each type of instruction, we can see that which control signals to be active and which to be inactive. We will further see the details of all these control signals in the upcoming slides as well. Okay. Uh, this slides, you can see that it makes a very important statement, which is pass control signals along just like the data. So extend each pipeline register to hold needed control bits for succeeding stages as well. Okay, it means that so the pipeline registers, uh, they do not hold only the data as well, okay, data and instruction. So they also hold the control signals, because for any processing it is very important to know that what are the values of different control which are required or at that particular stage. Okay, so in a pipeline processor, control signals are not only used immediately at where these are generated. Okay, since you know that in the single cycle data path, so the control signals are created and utilized in the same cycle itself. But in the pipeline processing, it is not the case. So where here the control signals are generated in ID stage, okay, and then these are stored in pipeline registers, and then these are passed forward. Okay, so this is exactly the same as how we pass the data through these pipelines. So these control signals are also passed by using these pipeline registers. Okay, so the diagram explain and it show that instructions entering the pipeline, Okay, and then there are the control signals, okay, and which pass from this stage to the next stage. Okay, and one of the key insight here, so you can see that the control signals are split into different groups. So based on the stage, based on which stage needs them. Okay, for example, you can see that first here is the execute group, okay, which contains four different control signals, and the details of each control signal we will see in the next slide. Then we have this memory group, and then we have this write back group. Okay, one thing important here, that you can see that uh, since all these control signals are generated here and then passed to the next stage, okay, then uh, the control signals which are relevant to this stage, they are utilized over here, and then the control signals which are to be used in the next stages, they are passed in the pipeline register to be used in the next stages. Okay, like all the control signals relevant to the execute stage are utilized over here, and then we have three control signals for the memory stage, okay, which are utilized over here, and then we have two control signals for the write back stage which are used over here. Okay, now uh, in this slide it shows a critical question, that if all control signals are generated in the ID stage, when do they actually get used for? Okay, when they are used. So the answer is the different signals are used in different stages, okay, and at the different time. So for example, as we see in the last slide as well, that we have three different groups of these control signals. One is this execute group, one is this memory group, and one is this write back group. Okay, so the execute uh, signals, control signals, which are generated here, are used one cycle later at this stage, okay, in the execute stage. So the memory signals which are generated over here, they are used two cycles later here at this stage. And the write back signals, they are generated over here, but they are used three cycles later in the write back stage. Okay, so this is being displayed, that where the signals are generated, all the control signals are generated at this stage, but for the execute they are used one cycle later. For the memory access they are used two cycle later, and for the write back they are used three cycle later. Okay, now we can see that there are the different control signals in each stage. Okay, and for what they are used, for example, this one, extended operation. Okay, so this control, either it is sign extension or it is zero extension. Okay, then we have ALU source, which controls that the selected source is for ALU input is, if it is 0, it is register B, and if it is 1, it is immediate value, immediate constant. Then we have 2 bits for the ALU operation, okay, and then we have destination register. These all are used for the execute stage. Okay, then here we have the memory write, which enables writing to data memory. Okay, and it is used for, for the store word instruction. Then we have this branch, which enables branch, and for the PC to decide that it to what source it to use. Okay, and then for the group 3 we have memory to register. Okay, that it selects data for register write, that either it should be ALU result or it should be from the memory, and then register write. A register write is which enables that writing to the register files. So this diagram is showing that for each stage and each different control signals group, where they are used, and what control signals they carry. Here we see the complete pipelined data path with the control signals, and it makes a very important statement here that control signals emanate from the control portions of the pipeline registers. Okay, so what does this mean? In a pipeline processor, control signals are not generated directly by a central control until the moments are there where they are used. Okay, so what happens that all control signals are generated once in the ID stage. Okay, and then they are stored in the IDEX pipeline register. From there they flow out to the EX stage, execute stage. Okay, and from then some signals are further passed forward to the this memory stage using this EX mem register pipeline register, and from those register they flow out to the memory and write back. Okay, so from here they flow out to the memory and write back stages. Okay, so, why this is important? Because they generated from this stage, and then they travel by using the pipeline register. Okay, and then at each stage they are used where it needs them. Okay. So each register, if you see each pipeline register, it has the two parts. One is the data portion and one is the control portion. Okay, so you can see this pipeline register. Okay, so it has this all one, which is the data portion, and these are the control portions, which holds the control signals. Okay. So similarly for this pipeline register also, it has the data portion and this control signals, and this one as well. It has this data portion and this control portions for write back. Okay. So again, in pipeline processor, control signals are generated once in ID stage. Okay, stored in the pipeline register, and then emanate from those register to the EX, mem, and write back stages. So ensuring each instructions has the right control signals at the right time. To understand further this pipeline processor design, this slide shows a simple instruction sequence, okay, that we will use to trace through the pipeline stages and understand that how pipelining works in practice. So the instruction sequence, we can see that it is the one load word, then we have subtract, then we have bitwise AND, then we have bitwise OR, and finally an addition statement. Okay, so why this example? Because it has some mixed instruction types. So it includes the load word, okay, which access the memory, and which have the R type instructions, which are subtract and OR and add. And then there are no dependencies. Each instruction use different registers. Okay, you can see, so no data hazards are there, and these are simple to trace because it is ideal for learning the basic pipeline behavior, that how it works for the independent instructions. Okay, so one another thing which we need to notice, that load word, it writes to $10. Okay, so I hope you already know that we are using the register numbers. Okay, so we can see, you can see in the register list, okay, MIPS register lists that this number is for which register. Normally it is like therefore temporary register or some register else. You can see that. Okay, then this instruction it is writing to $11. Okay, this one is saving the results in $12. This is in $13, and this is $14. Okay, so no other registers are using these register numbers. Okay, so these all are independent to each other. Okay, so what we will do in this example, so we will see the different pipeline timing diagrams, and we will track the values that how the data is being passed. Okay, and we will see that how the pipeline process work. Okay, and we will further see that how these instructions work in the pipelines. Okay. Okay, here in this slide, we have again the control signal tables. Okay, the reference table for the control signals, which we already discussed. Okay, so 5 stages are mentioned, and then the control signals for each instruction type are mentioned. Okay, why it is repeated over here? Because in other subsequent slides we will utilize it again, so it is just here to recall these concepts and control signals. Okay, so we will see that how these control signals are being generated and used. So viewers, we will start now the processing of these instructions. So what will happen in cycle one? So this slide shows the cycle one for our pipeline execution. So we are tracing the first instruction, which is load word. Okay, and this is in the first stage, which is instruction fetch. So in the cycle one, the first instruction is at stage one. Okay, and then you will see that in this these stages, like id stage or execute stage, memory stage, or write back, you will see that here it is showing that before instruction one. So of course, before executing these instruction of this program, so there might be something else which was processed. So this was okay, here at this stage there was something which was before this instruction, so here was something which was before two instructions, and here before three instructions, and here so four instruction before this one. Okay, so this is just showing that what was in these stages before this one. Okay, now, we already know that at this instruction fetch, it just fetch the instruction, and then it increment the program counter by 4. Okay, and then there is one multiplexer. Okay, and then this passed the data to this pipeline register in clock 1. Okay, now in the next, so in the next one, what we will see that there should be cycle 2. Okay, so in cycle 2, so what happens that now the second instruction also comes in. Okay, so the first instruction is in now in id stage, and the second instruction is in if instruction fetch stage. Okay, and then the rest of the stage are still you can say empty, not really empty, but for this scenario that there might be instruction which was before the instruction one. Okay, and there's something then two instruction before this, so this is showing that. Okay, here we can see that it generates these different control signals. Okay, so we can see that for this instruction, what instructions, what control signals are being generated. Here we can see that these control signals are highlighted. So we will see that what are these numbers actually. Okay, so the control signals, as you know, that these are generated in the id stage. Okay, and then packed into this pipeline register. Okay, and then they are further used and transferred into the subsequent stages where these are to be used. So as we discussed earlier, that there are different groups. So one group is this X execute group, and it has 4 bits. Okay, then we have the memory group which has 3 bits, and the write back group which has 2 bits. Okay, so if we see these all bits in each group, so we will see that here, since in the execute control signals, we have 0, 0, 0, 1. Okay, so starting from the leftmost, so this 0 is register destination, okay, which is RT. Then this 0 is ALU operation 1. Okay, and this is another 0 for ALU operation 1. Okay, this is for 1, this is for 0. Okay, and then finally this is the last one is ALU source. Okay, if it is 1, then it means that this is immediate, because we are dealing this instruction and it has this 20 immediate number, which is to for the offset of this address. Okay, so these 4 bits are for the execute stage. Now, there are these 3 bits for the memory stage. Okay, here again, this 0 is for the branch, so this is not a branch. Then there is 1. Okay, 1 means the memory, it needs to read from the memory. Okay, so this is enable, and then memory write is disabled, because in load word we are not writing in anything. Okay, so this 0, 1, 0 is for that. And then finally, with this write back stage, we have 2 bits which are 1 and 1. This one is for register write. Okay, and then one is memory to register. Okay, so write to register file, and then this one is write memory data. Okay, so this is also enabled, so both the bits are enabled for this one. So at this cycle, the first instruction in this ID stage, and then second instruction is this first stage. Okay, and then in the next cycle, okay, next slide, so now we will see that the first instruction is at the third stage at the execute, and then at the second stage we have this instruction subtract, it's over here. And in the first stage we have the third instruction. Okay, and now here also we can see that it generated these control signals. Okay, 1, 1, 0, 0. Okay, for this registration register destination, then ALU of 1, ALU of 0, and then ALU source. Okay, so these are the values for this. And for the memory, we have all 0, 0, 0. Okay, because it is there is no branch, no memory read, and no memory write, because this is subtract instruction. Okay, and here in the write back, it needs the register write is enabled, because it needs to write the result in this register. Okay, and memory to register, there is nothing for that. Okay, so these control signals are generated for this one. Okay, and then this cycle, in cycle 3, the ID stage generates the control signal for this subtract, this one, and execute. Here it executes this operation. Okay, and then here we have this instruction, which is AND operation. It is add instruction fetch cycle. Okay, in now in cycle 4, so you can see that the first instruction is here in the memory access stage. Second instruction is here at this stage. third instruction is here, and fourth instruction is in the first stage. Okay, and our WB stage is still empty, means if there is any earlier instruction, so that is here. Okay, and then we can see that how different control signals are being generated and passed, okay, for each. Like for example, for this instruction, when it reaches here at this stage, so it have its respective control signals which are relevant to the memory. Okay, and then the write back control signals are passed to the next stage by using the this control signal portion of this pipeline register. Okay. So all those we have already explained. Okay, so since this instruction is here, which is subtraction, okay, and it has these control signals, and then it is getting the opcode from the instruction, and so by using that function and these control signals, it generates the ALU operation. Okay, it generates that what ALU to perform. Okay, so it instructed from here. Okay, then in the next fifth cycle, now the first instruction, which is the load word, it reaches over here in the last cycle. Okay, so this subtraction instruction is here, the AND is here. Okay, the OR instruction is here, and the fifth instruction, which is add one, it is at the first stage. So you can see that what different control signals are at each stage which are relevant and to be used at the particular stage. Okay, so when it moves to the next cycle, which is cycle 6. So at this cycle, we can see that the first instruction is already completed. Okay, which was the load word, it's already completed, and the second instruction is at this final stage. Okay, then this instruction is at the memory stage. Okay, or instruction is at the execute stage. Add instruction is at the instruction decode. And now since we had only these 5 instructions, so now this is the empty for our this scenario. So if there is any instruction after this set of instructions, so it will come over here. So that's why it is after 1. Okay, so this is the first instruction which will be after completing our last instruction. Okay, so if we move to the next slide, in the cycle 7, the second instruction is also completed. Okay, so now you can see the third one is here. Okay, the fourth instruction is here, and the fifth one is here, and then you can see also the respective control signals of each instruction at the each relevant stage. And now you can see that this instruction decode stage is also empty with respect to our this current program. So it can hold if any other instruction which is after our last instruction, it will be over here, and then after 2 cycles, so whatever instruction, that will be at this stage. Okay, so like this, if we move to the next cycle, again you can see that what the it will execute, it will complete the third instruction, so fourth and fifth will be here, and then it will be uh, clearing the slots for the next instructions. Okay, and then in the cycle ninth, so it will complete this last instruction at this stage. Okay, and then these all stages will be empty with this with respect to over these 5 instructions. Okay, so we have completed the process of all these instructions. So lastly, here is the cycle time and CPI for a single cycle, multi-cycle, and pipeline design. So we can see here that for the single cycle design, the CPI is lower, of course, because in the single cycle, all instructions to be complete in one cycle, but the cycle time is longer. Okay. For the multi-cycle, the CPI is higher, okay, because each instruction it might takes multiple cycles to complete, okay. uh, its cycle time is short, but the CPI is higher. But in the pipeline design, it covers the deficiency of both these designs. So it cycle time is shorter and its CPI is also lower. So pipeline design is better if we compare it with the single cycle and multi-cycle design. So in today's class, we have covered a bit of data path and mainly the control signals in the pipeline processor design. Okay. Thank you. See you in the next class, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.